We're going to go through this big logistic regression example, building a model from scratch, building it up gradually, doing diagnostics and stuff on it, trying to interpret the coefficients. All the example is covered in detail in Regression and Other Stories in chapters 13 and 14. And at the very end, let me add this. I was working on this at the last minute. I never added it to the outline. So let's just add it now. Talking about how to assess model performance for a logistic regression model as a classifier. There are two concepts: calibration, which is how accurate are your probabilities, and discrimination, which is how good are your guesses based on your probabilities. We'll go over those later. Just a refresher from last time on the whole idea of logistic regression, which is if you want to know the probability that an outcome is 1, given that the covariates x are equal to some values, you just stick a linear model, a plus bx, inside this inverse logistic function thing so that it gets bounded between 0 and 1. So as x gets bigger and bigger, a plus bx would stretch off to infinity and to negative infinity, right? It would just get bigger and bigger, way more than 1, not make any sense as a prediction for y if it were linear. But then when you stick it inside this logit inverse function, it just makes it gradually approach but never exceed 1, and gradually approach but never exceed 0, as x gets really big and as a plus bx gets really big. So yeah, so whatever your x value is, and it could be multivariate, you take that linear function of it and take the logit inverse of that. This gives you some value between 0 and 1. That's your estimate of the probability that y is equal to 1. That's the general idea of logistic regression. Here's how, with linear regression, we did that little bit about how R does it under the hood. We'll do that here too. You won't really need to use this. Like with linear regression, you can get some insights into what's going on and why your model is behaving the way it is. If it's behaving weirdly, by being familiar with this, and it's maybe also a rite of passage. I don't know anything about cars, so if a warning light goes on with my car, I usually just ignore it, but the other option would just be to take it to the mechanic, and that's probably also a crazy thing to do a lot of the time. Most of the time, it would be nice if I just knew what it meant and could react reasonably. That's what knowing what R is doing under the hood when it's fitting a regression model might sometimes allow you to do. So here's how the parameters of the logistic regression get fit. The parameters are a plus bx. You want to find the best a and b that fit the data as well as possible, just like with the linear regression. Your data are a bunch of x's and a bunch of xy pairs. You see their outcomes, and you want to find the linear function of the covariates that leads to the probability estimates for the outcomes that are most compatible. How do you actually define that? The likelihood, the probability of observing the outcomes, y, that you actually observe, given some candidate values for the parameters, like the coefficients of the x's, and also given the x's, is the product over all of the observations, like all the people from I equals 1 to n. If the outcome was equal to 1, it's the probability that it was equal to 1 under the model. That's what the model says is the probability that y is equal to 1. It's logit inverse of xi beta, just that linear function of x or beta. And if y is equal to 0, then it's the likelihood of that under the model is 1 minus the probability that y equals 1 given x, according to the model. Another way to write this out is just if y is equal to 1 and you take something to the y, it just is that thing, right? And if y is equal to 1, 1 minus y is 0. And so you're just multiplying by 1, and that like erases this term from the product. So this is just another way to write this. It's just saying it's the product of for each person. If y equals 1, their estimated probability, or like what their probability would be under the model of y equaling 1. And if y equals 0, it's what's their probability under the model of y equaling 0. And you want to find the beta values that maximize this, that make the observed data most likely. You want to find the beta values that give you high probabilities that y equals 1 when y equals 1, and low probabilities that y equals 1 when y equals 0. That's the whole idea behind logistic regression model fitting. And in practice, it's just done by setting the derivative of this likelihood with respect to beta equal to 0. Like in calculus, if you want the minimum or maximum of a function, you take the derivative, you set it to 0. And there's not like a closed form solution, meaning there's not like a formula that gives you the answer the way there was with linear regression. R uses this like iterative numerical approach. I think it's usually Newton-Raphson is what it's called, that approaches the answer and then eventually arrives at a solution. But you don't need to know any of that really. It's just to expose you to it. For a very large X, the estimated probability is going to be either near 0 or near 1, because if you look at this curve, if X gets large enough, it approaches 1 or it approaches 0. This could also be flipped if it's a negative association. That means that if you're wrong about the value of the person's outcome at that point, the estimated probability of the observed outcome is going to be basically 0. So for a really large X, let's say you have an observation out here and it's 0. There's someone with an outcome 0 and an X of 25. Then what would the contribution to this likelihood that you're trying to maximize be if you have parameter values that make the predicted probability 1 at that point? It would be 0. So you'd be multiplying this product here by, you'd have a 0 term in there. The probability of y equals 0 is 0 according to these parameter values. And so that would completely demolish your likelihood. You're trying to maximize it. That would make it as small as it could possibly be. So it becomes very important to get that prediction. If you have one very extreme X value, you're going to have your curve approach their observed value, or else your likelihood will be very small. And the whole point, or the whole way it's fit, is to maximize the likelihood. So that's just an example of how understanding maximum likelihood can give you a little bit of insight into the behavior of a model, but again, not super important, just exposing you guys to it. Now we're just going to go through at length an example that Gelman and Hill and Atari go through at length in Regression and Other Stories, chapters 13 and 14. They look at data from this study where researchers measured arsenic levels in a lot of wells that people use for drinking water, like their personal wells in Bangladesh. And they told residents if their well was unsafe. And then several years later, they came back and they recorded which residents with unsafe wells actually switched wells, like started using a neighbor's well. And they also recorded predictor variables that might be associated with whether or not they switch. So, for example, distance from the nearest safe well, the arsenic level in their well, their years of education, and their involvement in community organizations. This is what the data set looks like. Whether they switch, that's the binary outcome. Arsenic level in their well, their distance from the nearest neighbor's well, whether they're in community associations, and their education level. Here's a map of the data. The dark points are unsafe wells, and I think the light points are safe wells. Usually if you had an unsafe well, you're not too far from some place that had a safe well. Like they're all interspersed, they're all mixed together. It's not like there's a broad swath that would be unsafe. Okay, so the first thing that they consider is fitting a model for whether or not you switch with distance from the nearest safe well as the only predictor. Here's the R code that summarizes this model. First, they defined a variable distance in hundreds of meters instead of just distance in meters to make things a little kind of easier to deal with. So that's what dist 100 is. Dist 100 equal to 1 would mean that you're 100 meters from the nearest safe well. And here is the summary. The farther away that you are from the nearest safe well, the less likely you were to switch, which makes sense, I think. So if we interpret the coefficient, logit inverse of 0.61, which is the intercept, equals 0.65. That means that the probability of switching if you live right next to a safe well, meaning when dist 100 equals 0, is 65%. And so the average distance in the data set is 48 meters. So 0.48 for dist 100. And if you are curious what the association between an extra unit of dist 100 and probability of switching is in people at the average, you can look at the probability of switching if you're 1.48, so distance away, that's one above. Here, the 0.62 is coming from here, and the 0.61 is coming from here, minus the probability of switching if you're at the average distance, and that's 15%. Your probability of switching drops by 15% if you're 100 meters further away, or residents who are 100 meters further away than the average were 15% less likely than those who are the average distance away from a well to switch from a safe well. So the next thing that they did when they're building up this model is they considered adding arsenic as a predictor. So the arsenic level in your unsafe well. The directions of the coefficients make sense again. The farther away you are from a safe well, the less likely you are to switch wells. And the higher the arsenic level in your own, the more likely you are to switch wells. And both of these coefficients are pretty highly statistically significant. The standard errors are very small compared to the magnitudes. The AIC went down in this model compared to the previous model. So now it's 3936. In the previous model, it was 4080. The AIC is this formula. It's the Akaike information criterion. It's -2 divided by your sample size times the log likelihood. We talked about how you're trying to maximize the likelihood, right? And so negative something times the likelihood means that you're trying to minimize the AIC because you want the likelihood in your model to be as high as possible. But then you're also adding, as part of this formula, 2 times the number of predictors divided by n. So there's this penalty factor for adding more predictors, because if you add more predictors, you're always going to increase your likelihood. You'll be able to fit the data more closely and get a better likelihood. At what price? AIC is a really crude approach to determining if it was worth it to have a more complicated model versus a less complicated model. There are other competing formulas like this. They all can be proven to give you the best model in a set under assumptions that never actually hold. So how you choose among them is somewhat arbitrary. Another option other than these information criteria is, in regression and other stories, they recommend using leave one out cross-validation. So basically fit your model leaving out each observation and then use the model fit to all the observations that you didn't leave out to predict the observation that you did leave out and see how well, on average, you're able to predict the observations that you didn't include in your model. And I think that does have better kind of properties in terms of being more likely to make you arrive at actually like the most stable model with the best predictive power out of sample that generalizes best, but it's not as straightforward to do. It's R just spits out this AIC thing. So you might as well, for low stakes cases, usually it won't matter too much. It's a nice rough indicator of whether it was worth it to try a more complicated model. In this case, it says it was worth it to add arsenic to distance. It helps you predict better, and it was worth like the added complexity of an extra predictor. That logistic regression line as a function of that variable, fixing the second variable at one value. So if arsenic is 1, here's how probability, that's what this top line is, here's how probability of switching changes as distance grows. And then they did the same thing for when arsenic is 0.5. So this is how you can visualize the combined associations, or like the joint associations between the two covariates and the outcome. By looking at the difference between the two lines, you see the association between arsenic and the outcome at any given value of distance. And for each value of arsenic, the whole line gives you the association of distance at that value of arsenic. And then they reverse it here, where they pick two values of distance, 0 and 50, and show the relationship between arsenic and probability of switching at each of those two distances. And this can be like a nice, useful way if you have two predictors to visualize. At any given distance, the difference between the two lines is the association between arsenic and the outcome at that distance. The gap between the lines shows the non-causal impact of arsenic on the outcome across distance levels. The next thing is adding an interaction term. When you add an interaction term, you get still the main effect for distance is farther away, less likely. Same deal, main effect for arsenic is the higher your arsenic, the more likely you are to switch. And there's a negative interaction that's not statistically significant, but maybe a little close, which says that as your distance increases, the impact of your arsenic level decreases. Okay, so let's try to interpret the coefficients. It's going to be a little messy. After we go through this exercise of confusingly trying to predict the regression coefficients, they also give some alternatives for better ways to interpret. In particular, one way is centering all the variables before you fit the model, which we had talked about with linear models, also giving a more natural interpretation to the coefficients. And then another way is to not really stare at the coefficients at all, but to do things like average predictive difference, which we'll go over. Okay, but first, let's just go through this exercise of trying to figure out what these coefficients mean. So the intercept is negative 0.15, right? So logit inverse of negative 0.15 is 0.47. So this is the probability of switching if distance and arsenic are both 0. So if you're right next to another well and the arsenic level in your well is 0, but this makes no sense because arsenic was always greater than 0 and everybody's well in the sample because it's only people who had unsafe wells. So you can't really interpret it. So instead, maybe what you might be interested in is just what's the probability of switching if you have the mean distance level, which is 0.48, and the mean arsenic level, which is 1.66. So just plugging those into this regression formula, you get that the probability is 59%. So now you could look at the distance coefficient. That corresponds to comparing two wells that differ by 1 in distance in units of 100 meters. If arsenic is 0, so that this interaction term doesn't contribute anything. But again, that doesn't make sense, right? Because arsenic is never 0. So instead, what you might be interested in is what's the coefficient for distance at the mean arsenic level? It would be negative 0.58 minus 0.18 times 1.66. So that's negative 0.88, right? At the mean arsenic level, when you combine like the interaction and just the coefficient for distance on its own, you get that a change in one in distance would reduce the linear function of the covariates, not on the probability scale, by 0.88. So what does this correspond to on the probability scale? There's this divide by 4 trick that they talk about in the book, which gives you a way to interpret these coefficients approximately on the probability scale. So you just divide them by 4, and then that tells you about what the impact of moving it by 1 would be if it's near its mean. They explain in the book, it's just an artifact of the logistic function that if you take its derivative near the mean of the covariate, so near the middle of the logistic regression curve, it'll be about that coefficient over 4. It's just like a weird mathematical thing that just happens to work. And it's just a nice thing to use to quickly interpret a regression coefficient, but it's not worth deeply understanding, I don't think. So we can divide 0.88 by 4, and that tells you then that at the mean arsenic level and near the mean distance, each 100 meters in distance is associated with about 22% lower probability of switching. Now we can look at the arsenic coefficient. Let's look at that at the mean distance. At the mean distance, a shift in 1 in arsenic would shift on the non-probability scale the output of the linear part of the model by 0.55 minus 0.18 times 0.48, which is 0.47. And again, using this divide by 4 trick at the mean, this says that at the mean distance and near the mean arsenic level, where the divide by 4 trick is applicable, each added arsenic unit is associated with about 12% higher probability of switching. And then the interaction just tells you that the association between arsenic and switching diminishes as distance increases. The farther away you are, the less having higher arsenic increases your chance of switching. So centering variables makes all of this easier. So that was a lot of work combining coefficients and stuff. If you just subtract the means from each of these variables, so take the distance variable and subtract its mean in the data set. So you have a new variable that's centered distance, and do the same to arsenic. Subtract the mean arsenic value from every entry in the arsenic column, and then just fit the regression to centered distance and centered arsenic as the covariates. Then this is what you get. And so the interpretation of the coefficients becomes much simpler. So the constant term, the intercept, is the estimated probability of switching if the centered distance and the centered arsenic variables are both 0, meaning they're both at their means. So that's exactly what we wound up computing previously as like the best interpretable thing we could come up with, but with more effort. Here it's just direct. Same, the coefficient for distance is on the Logit scale. If arsenic is at its average value, meaning C arsenic is 0, the coefficient for distance tells you the association between a unit change in distance and the probability of switching. Because when arsenic is at its mean, then this interaction contributes nothing because C arsenic is 0. And obviously the arsenic main effect contributes nothing as well. So again, you could divide by 4 to get negative 0.22, as we did before. Same deal for arsenic, right? That the coefficient for arsenic level, if the distance to the nearest safe well is at its average, is how you would interpret the centered arsenic coefficient. So again, we do the same thing we did before, but it's just immediate, and the interaction term isn't impacted by centering. And also all of the model predictions stay exactly the same when you center the variables. It just helps with interpretation. And so up top, we have those 2 double line plots that I showed you before. where you plot how probability of switching changes as distance changes for if you fix arsenic at two separate values. You can do the same thing for the interaction model and see how things change. And for the most part, they don't change very much. That interaction term didn't really alter these plots too much. The most obvious way in which it did alter it is that the impact of arsenic kind of disappears at somewhat lower distances in the model that has an interaction than in the model that doesn't have an interaction. When you have an interaction, the arsenic level stops being associated with probability of switching at distances a little over 200, whereas if you have a model without interactions, arsenic is still impacting probability of switching at these distances. But overall, it's not really impacting the model too much. Another thing you can do to interpret not coefficients, but just what the model says about the association between a variable and the probability of the outcome. So for example, distance from the nearest well and whether or not you switch, is you can just take the average over everyone of their probability of switching if you set their distance equal to some value, and then take the difference from if you set it to some other value. So the difference between if dist 100 equals 1 and 0, the difference in average probability of switching. It's the same thing as standardization, it's just not causal. You're just setting everyone in the population or in the cohort's value for a certain variable to be one thing, computing the predicted probabilities if it were that thing, setting it to be another thing, computing the predicted probabilities if it were that other value, taking the difference. You could instead average and then take the difference of the averages. So it would be the same. This is a nice way to kind of marginal over the cohort, averaging over everyone because of the nonlinear nature of the logistic curve and because of interactions and stuff. The association between the change in a covariate and the probability of the outcome being 1 can be different, very different for different people. Looking at coefficients alone is often not very illuminating, but looking at this just average over everyone of what's the association in each person given their covariates can be more informative. Increasing distance by 100 meters on average decreases probability by 22% in the cohort, and increasing arsenic from 0.5 to 1, or comparing 0.5 to 1 on average across the levels of the other covariates in the cohort would increase probability of switching by 12%. Because there's nothing about exchangeability here. Exchangeability is what allows you to interpret things as causal. Standardization is what allows you to combine the causal effects within each level of the covariates, like each of those conditional causal effects, into an average effect. But the causal part isn't coming from that averaging that we're doing here. The causal part comes from conditioning on covariates that make treatment exchangeable with the outcome, such that treatment is exchangeable. I'm just saying you can do this even when you're not trying to estimate like the causal effect of distance. So even if you don't think that X here controls for confounding between distance and the outcome, you can still go through the procedure of standardization, and it gives you like a useful summary of the association between distance and the outcome that you don't think is causal. Let's get to model diagnostics. So with linear models, we looked at residual plots, where we would plot the predicted value, the conditional expectation of the outcome, against the residual, which was the difference between the actual observed value of the outcome and its estimated value. If you do that for a logistic regression, it's non-informative. It will look like this, because the outcomes are always 1 or 0. So as the predicted value goes towards 1, either you were right that it's 1, in which case the residual is going to be 0, or you were wrong that it was 1 and it's going to be -1. Similarly at 0.5, either it was 0 or 1. If it was 0, then your residual is going to be -0.5. And if it was 1, then your residual is going to be 0.5. So you're just going to have these two lines, which doesn't really tell you anything about whether the model was fit properly or not. There's no looking for a pattern in the shape. It's just always going to look like this. However, if you take averages of the residuals in bins, in any given bin, the expected value for the residuals, if the model is properly specified, is 0. If the model is properly specified and you're like predicting 99%, it should be the case that 99% of the dots here, the residual would be 1%, observed minus predicted. So it would be 1 minus 99%. And then you have a few zeros where the residual is 1. Those should average out to 0. Similarly, like at 0.5, you should have the same number of 1s and 0s, the same number of residual equals 0.5, and the same number of residual equals -0.5. And their average should be 0. There's going to be random variation in bins that have a finite number of points in them. It's not always going to be exactly 0, but the difference from 0 should also be random. So when you take bins and take the average residual in each bin, you get back this scenario where you expect a random cloud, and if you see a shape emerge, then that's a sign that your model was not properly specified. And what I mean by taking bins is like splitting up the x-axis here into little segments. And here you have all the residuals. You could split up the x-axis into little segments and just take the averages of the residuals in each segment. Like each segment would contain a bunch of points, and you could just take the average of all of those points. And the expectation of within any given group of points that are near each other is that their average is 0. But they all randomly not be 0 because it's a finite number. Just due to random variation, the residuals will sometimes be negative. The bin residuals, the averages in these bins will sometimes be less than or greater than 0. But it should be random. So you should have a cloud. And it should be shapeless, just like before with the residual plot from a linear model. Just like with a linear model, you don't have to plot the predictions against the residuals. You can also plot covariates against residuals. And Gelman did this here with distance and arsenic level in the Wells example, and found that the distance bin residual plot looked good, but the arsenic one looked bad. So there are some issues. Like at very low levels of arsenic, there was a very large residual for one thing. It was off by a lot there. And also there's a pattern to it where it tended to be greater than 0 at lower levels and then dip down at higher levels. And to Gelman, that suggested that taking a log transformation might be helpful. In general, if you have a nonlinear relationship, it's worth trying various transformations. He somehow realized that log would be good here. I wouldn't have realized it, but inspired by the irregularity in the residual plot, he did a log transformation of arsenic and refit the model with log arsenic. And then the residual plot looked better. There's still this issue, but to a lesser degree with that residual, but there's no pattern anymore at all. Another thing that you can do to assess a model's fit is a calibration plot. This is very related to a bin residual plot. Your model is well calibrated if the outcome is actually 1 p% of the time that your model predicts that the probability that the outcome is 1 is p%. So basically your probabilities are right. An example is if it rains 40% of the time, you say that there's a 40% chance of rain, then your predictions are well calibrated. It means that when you say 40%, that really means 40%. Now, calibration isn't everything. Suppose it rains 40% of the time, like in Seattle, I guess it might be that rate, I'm not sure. But every day, suppose you say that there's a 40% chance of rain. That's always your guess. Then your predictions are going to be perfectly calibrated. Every day you say 40%, overall there is a 40% chance of rain. So 40% of days overall it does rain. So you're perfectly calibrated, but also completely uninformative. You were just saying the base rain rate every day. There is nothing about any given day that made you say 40%, and you never deviate from the overall average. So that's just to say that calibration is a desirable property, but you also want to be informative, right? Here's the calibration plot for the well switching model. On the x-axis is the prediction, so the predicted probability that y equals 1. And for deciles here, the calibration plot assesses what proportion of the observations who you said would have probability 0.2 were actually 1. What does the calibration plot tell you? For each point on the x-axis, that corresponds to a decile. It's saying for the decile of predictions centered at that point. So basically, for all the observations where you predicted about 0.45 probability that y equals 1, taking those observations, what proportion actually had y equals 1, and that's the y-axis. And these two should be equal to each other if your model is well calibrated, and that's what this 45-degree black line represents. And so if all the points on the calibration plot are hugging this black line, that means that you have a well-calibrated model. It means when your model says that there's an 80% chance that y equals 1, there's actually an 80% chance that y equals 1. So a calibration plot is a good way also to assess a model that you fit. But as I was saying, calibration isn't everything, right? You can be perfectly well calibrated without being at all informative. So another thing that you might want to look at is error rate. For example, let's say you use your model to make binary guesses. In the well example, you might guess who's going to switch, or you might guess that someone will switch whenever the predicted probability is greater than 0.5, but you're not focusing on your probability estimate. You're just focusing on a yes/no guess. If that's what you're doing, the error rate is just the proportion of your guesses that would be wrong if you followed that rule. In R, you could compute this as the mean of the indicator for whether you guessed greater than 0.5, but actually there was no switch, or your model said less than 0.5, but there was a switch. In the case of the well switching model, this comes out to 0.37. The error rate is 0.37. So if you follow this rule of guessing switch whenever probability is greater than 0.5, you'll be wrong 37% of the time. So you could compare that error rate to the error rate of a null model, where a null model includes no predictors. So this gets a sense of how informative your model is. The null model in the predicting rain example, if it rains 40% of the time, the null model just says, okay, 40%. You'd guess 40% for every day. And if you're for a model to be informative, it should outperform the null model. So again, in the Wells case, the error rate was 37% when we fit the model. But if you just fit a completely uninformative model with no predictors, the error rate is 42%. And this is not a huge difference. So while the model was well calibrated and certainly gives you some information about switching behavior and associations, it doesn't have good discrimination. It doesn't discriminate switchers from non-switchers very well. Another way to assess the performance of a model is to look at what's called the confusion matrix. So for a given threshold above which you guess 1, for a given probability estimate threshold, let's say 0.5, you look at the number of people where you would guess 1 and it would actually, the outcome would actually be 1, they actually switch. You guess 1, but it's actually 0. You guess 0, but it was actually 1, and you guess 0 and it was actually 0. And from this confusion matrix, you can compute the sensitivity and specificity, where the sensitivity is the probability of guessing one, given that it was actually one. How sensitive are you to the true ones? And that's just 1345 over the sum of 1345 and 392 here. So the sensitivity is 77%. And the specificity is the probability of guessing a true zero, given that it actually was zero. So that's just 728 over 728 plus 555 in this case. So specificity is 57%. The sensitivity and specificity depend completely on the probability threshold that you use. And you could imagine varying that threshold to be very low or very high. So if you have a very high threshold for guessing one, then you're going to be very insensitive, right? Your sensitivity will go way down. You'll very rarely guess one, so you'll miss a lot of actually ones, and your sensitivity will be very low. But your specificity will be very high because you'll almost always guess zero. So an ROC curve plots sensitivity against specificity for the whole range of probability thresholds that you might use. And I was just illustrating there's a trade-off between sensitivity and specificity as you vary the threshold. And you can see this in the plot here too, where as specificity goes down, sensitivity goes up, right? Ideally, you want to have sensitivity and specificity both be one, right? For a given specificity, you want to have as much sensitivity as you can have. And for a given sensitivity, you want to have as much specificity as you can have. So you want this curve to be as close to this square here as it could be. And a way to assess how well the model discriminates is to look at the area under the curve. Because again, you want this as high as it can be at any given point, right? So for any given specificity, you want sensitivity as high as it can be. So a way to assess how well you're doing at that is to just look at the overall area under this curve. This curve will always do better than a straight line, which corresponds to just random guessing. Random guessing will just give you the straight line, or an AUC of 0.5. So the AUC should always be greater than 0.5. It also has this interpretation as the probability that if you're presented with a random y=1 observation and a random y=0 observation, that your model will assign a higher probability to the y=1 observation of being 1 than it would to the y=0 observation. So if you're just repeatedly given a random pair of observations, one has y=1, one has y=0, what proportion of the time do you assign a higher probability of y=1 to the actual y=1 observation? You want that to be higher, right? That's a measure of how well you discriminate between the y=1s and the y=0s. So AUC measures discrimination as distinct from calibration. Calibration and discrimination are the two main properties you might want a classifier to have, which a logistic regression can be. You can use it to classify ones and zeros. You want your probability statements to be well calibrated. If you say a certain probability, you want it to really be that probability. But you also want to be able to tell the ones from the zeros, given the covariates as well as possible. And that's discrimination. You should really do this on a test set, not on the training set, because it's cheating to be able to discriminate well on the data that you actually used to learn your model.